Okay, this is kind of boring, but it's easy. I want the graphing I want to make as insufferable as I possibly can, and the best way is going to be if we kind of give this a shot here. Create a table of how you would graph that equation. Well, what's special about the x? Well, how about the fact that it's in a square root? Okay, I think that makes it special. So if your x is in a square root, here's what you want to do. You want to put a 0 in the middle, and then you only want to go up by perfect square numbers. So the first perfect square is 1. And then 2 times 2 is 4. I know 4 is a perfect square. Then 9. I could do 16. I usually just stop at 9. Now, can you have negatives in square roots? Well, let's see if I can on my calculator. Nope, you can't, unless you have to do the I, and I will not show up on a graph, so you just put stop right there. Okay, then here's all you do. You just plug in for x. So you got -2 as your multiplier, and I'm going to put 9 in the calculator, and then to tell my calculator that, gee, that's a square root, we need to take it to the 1/2 power. That's how I'm going to be doing it. There is another way to get a square root, so your y output's -6. Okay, now let's insert the 4 in. Times 4, and I got to tell my calculator that needs to be the square root of 4, so I take it to raise it to the 1/2 power. Now these do form patterns here. Okay, that is indeed going to be -2, and that's going to be 0. Okay, so you're good there. All right, now the next one. What I want to do first is rewrite this equation, okay, so that this -4 is not even a part of it. I'll worry about the -4 here later. Okay, now I'm gonna make a note. Remember the -4. Okay, so here's what I do. It's a square root, so again, I'm only going to pick perfect square numbers, and we can't have negatives in square roots. Okay, so let's put 9 in. So 3 times 9. I got to tell my calculator that that's a square root of 9, so I take it to the 1/2 power plus 6, and that's 15. Okay, 3 times 4 to the 1/2 power, and it's really, some of these are not hard to do mentally, okay? You put a 4 in a square root, well, you know the square root of 4 is 2. What's 2 times 3? 6. Add 6, you get 12. Okay, and then we get 9 and 6. Now, remember the -4. Here's what you need to do now. You need to you need to do what's called compensating. How would you overcompensate for a -4? Huh? How would you cancel that out? If you didn't want it there, how would you cancel a -4 out? You would +4. So what I need to do is +4 to all these. So that's going to be 13, 8, 5, and 4. And those are going to be our actual input numbers into the equation. Here's why. Because now because you see, if I put in 9, if 9 minus 4 is 5, and the square root of 5 is something crazy. But now that I have x is 13, 13 minus 4 is going to give me the 9, and then 9 is a perfect square root. It's 3, so I get a nice round number there, okay? So that's how I handle it when something's being added or subtracted to my x in there. I just forget about it, but then I go cancel that out with my x variables. Because again, having a 9 in there, 9 here is okay, but this was the equation. 9 minus 4 is 5. Square root of 5, I mean, that's crazy. That's like 2.23 forever. But now that I have 13, 13 minus 4 is 9. Same thing, 8 minus 4 is 4. 4 is a perfect square. 5 minus 4 is 1. 1's a perfect square. 4 minus 4 is 0. 0 is always a good one to have. Okay, as I move along, let's go to some cubes. Now you're going to pick perfect cubes. So the first perfect cube is 1. Then 2 times 2 times 2 is 8. 3 times, and then 27. Now, unlike the square roots, you can put negatives in cube roots. So we don't stop there. It goes on in both directions. Okay, now there's nothing in with the x, so that's good. So I'm going to go 3 parentheses, and I'm going to put 27. Now to tell my calculator that's a cubed root, I raise it to the 1/3 power, and then minus 6 gives me 3. Again, the cubed root of 27 is equal to 3. 3 times 3 is 9. 9 minus 6 is 3. Then we'll put 8 in to the 1/3 power, and then minus 6. That's the cubed root of 8. That's 0. Okay, now I'm recognizing a pattern. Then it goes down by 3s. Negative 3. Okay. Negative 6, negative 9, negative 12, negative 15. Okay. And there's nothing there I needed to take out, so that's going to be what I go with. And it never ends. The domain's infinite. Okay. See here, the domain stopped at 0 to all the positives, but on cubed roots, it's infinite. Okay, cubed root, but we want to take out that plus 5. And I'll worry about that later, but I need to rewrite the equation so it's just x, the cubed root of x. And I'm just going to write to myself, remember the plus 5. Okay, so it's a cubed root, so then I go 1, 8, 27, and we can have negatives as well in those cubed roots. Okay, so this is where I'm going to plug the numbers in for, because I don't really want that plus 5, because 27 plus 5 is 32, which is not a perfect cube. It's going to give me a horribly sloppy answer. So negative 4 times 27. Then I need to raise it to the 1/3 power, and then plus 10. Okay, so that gave me negative 2 as the output. Negative 4, and then 8 to the 1/3 power, plus 10. I got 2. So this looks like it's going up by 4, so that's going to be 6. It's going to be 10, 14, 18, 22. Okay, now the outputs are a done deal, okay? But now we got to remember the plus 5, because if I actually put 27 in here, that's not going to work, okay? Because 27 plus 5, the reason this worked out so smooth here is because 27, when placed here, is a perfect cube. It's equal to 3. And then times negative 4 is negative 12, plus 10 is negative 2. However, there was a 5 being added, so I don't want that 5 being added. So I need to do the opposite of plus 5, which is to minus 5 from every single one of these inputs. So that's 22. That's going to be 3, negative 4, negative 5, negative 6, negative 13, and negative 32. Okay, now 22 plus 5 gives me the 27 that I want in there. Okay, 3 plus 5 gives me the 8 I want in there, and so on. Okay, so that's kind of what you're doing. Okay, hit a couple more here. Okay, it's a square root, so now I'm picking I don't want the plus 3 in, though. I want to rewrite this so it's just the square root of x minus 6, and I'll need to remember, compensate for the plus 3 later, okay? So it's a square root, so perfect squares 1, 4, and 9, and you don't have negatives. Negative numbers are not perfect squares. They are perfect cubes, but they're not perfect squares, so stop. Okay, so 4 to the 1/2 power. To tell your calculator it needs to be a square root, you raise the number to the 1/2 and then take away 6. You could do this mentally too. Square root of 9 is 3. 3 times 4 is 12. 12 minus 6 is 6. Boom. And the square root of 4 is 2. 2 times 4 is 8. Minus 6 is 2, I'm guessing. So it goes down by 4s, so we're going to get -2, -6. All right, now there was that +3 that we don't want there because 9 plus 3 is 12. That's not a perfect square. So what I can do is -3. You do the opposite. So that's now 6. And 6 plus 3 will give me the 9 there that I want. 1, -2, -3. That's the point of that, because now I can know that this is the table that would represent this equation as easily as possible. Okay, now you're dealing with cubes here. So cubes, you got 1, 8, 27, and negatives are also perfect cubes as well. Okay, so we're going to take out that -4. Okay, so -2 times 27 to the power of 1/3 makes it a cube, plus 10. I got 4. Okay, now I get another number that tells me the pattern, -2 times 8 to the power of 1/3, because that tells the calculator it's a cubed root. That's 6. Well, easy pattern, 4, 6, 8, 10, 12, 14, 16. Okay, now the -4, I need to compensate for that being there. So I +4 to all these. I do the opposite. It's not that you want a -4, you want to overcome the -4, so you would add 4 to all of them. So that's going to be 31, 12, 5, 4, 3, -4, -23. Okay, there's the table.